Hello everyone, welcome back to your favorite and India's most affordable learning platform, Physics Wallah. So in the last session of thermal properties of matter, so where we have discussed the equivalent conductivity in series combination of the rods and parallel combination of the rods, right? And what is the equivalent thermal resistance, right? And we have solved some questions related to that. And I gave some questions as a homework for you. Hope you guys solved them. Okay, chalo. So today we are going to deal with the lecture number 6, where in the lecture number 6 we will deal with the emissive power, so the absorptive power and Kirchhoff's law also. So these three are our main objectives for today's session. Okay, as usual guys, I just need your attention for the next 1 hour. Just be with me, avoid all the disturbances around you, and at the end of the lecture it's very important to prepare your own short notes. And one more thing, competitive examinations are around, so you guys have to speed up your preparation. So if you are in class 12th or a dropper, so you should attempt more test, more of revision, make the short notes, revise it daily. Okay, attempt the previous year questions. So this is very important. Yes, chalo. So first let's recall the previous class formulas. So then we'll go for the today's concept. So first of all, the equivalent conductivity in the series combination and in the parallel combination. So let's say in the series combination of rods. In the series combination, hope you guys remembered the thermal resistance formula RH, right? So which RTH, which is nothing, which is equals to L by Ka, right? So first, what is a series combination? So when two rods are connected end to end or face to face like this, so then there will be junction temperature theta, here T1 and here T2. Obviously you know that T1 is greater than, theta is greater than T2. So let's say this material has length L1 and this has length L2, and this has thermal conductivity K1 and this has the thermal conductivity K2, right? So then we have already discussed that, so whatever the heat flows from here, so the same heat flows from here, so heat current, so the same heat current flows from here, right? So what is that heat current formula? H by T, Ka delta T by L, right? Chal. So here I can write H is equals to Ka delta T by L. Yes, this formula also we know. And here the H1 is equals to H2 is equals to H. Yes, yes. So then we have also wrote, so that let's say the thermal resistance of the first conductor is R1, the thermal resistance of the second conductor is R2. So here R equivalent will become R1 plus R2 in the series combination of rods, right? And then, so what is the formula for the equivalent conductivity? K equivalent is equals to L1 plus L2 by L1 by K1 plus L2 by K2, and goes on. This is a equivalent conductivity in series combination of the rods. So this is about the series combination, and we have also seen the parallel combination. So let's write the parallel combination of the rods formula. Done? Chal. So let's see. So here let's say we have two rods. So this is the one, and then this is one more. So from here, so the heat is coming, so this heat will be divided into this and will be divided into this, right? Chalo. So then let its cross sectional area A1, let its cross sectional area A2. So then the heat will be divided in this, so the heat current. So the H is equals to, I can write, so the H1 plus H2. The total heat current H is equals to H1 plus H2. So and what is the R equivalent in this case? So the 1 by R equivalent is equals to 1 by R1 plus 1 by R2. Yes, and what is the K equivalent? So it's K1 A1 plus K2 A2 by K1 A1 plus A2. So this also we have studied, right? Chalo. So and then if they have the same cross sectional area, then what we can do? K1 plus K2 by 2. Yes or no? So if they have the same cross sectional area, so then we can write K1A plus K2A. So by A plus A 2A. So A, if you take common, A will cancel, and then K equivalent will be equals to K1 plus K2 by 2. So for the conductors having same cross sectional area, two conductors, if they are connected in the parallel combination like this, and if they have same cross sectional area, this will be the formula, right? Done. Chalo. So next, so let's go for the next one. This is the previous class topics, right? Chalo. So now I gave these questions as a homework for you. So let's try these questions now, guys. Hope you solved it. So if you are not getting, just follow the procedure that I am going to do here. So what's the first question says here? A cylinder of radius r of thermal conductivity K1 is surrounded by a cylindrical shell of inner radius r and outer radius 2r made of thermal conductivity K2. So the two ends of the whole system are maintained at, so ends of the ends of the whole system are maintained at two different temperatures, so T1 and T2. So fine. So where T1 is less than T2, so let's say this temperature is T2, let's say this temperature is T1. Fine. So the system is in steady state and there is no loss of heat across the cylindrical surface. Fine. So the thermal conductivity of the system is, so what they are asking finally, so the thermal conductivity of the system. So first you have to understand this statement. So it's a shell of inner radius r and outer radius 2r. So what does that mean? So just imagine here we have one cylindrical rod and inside that there is one more conductor that is placed. So the total cylindrical shell has 2r radius and the inner conductor, it has r radius. That's it. So if you supply the heat, so that heat will, see here, if you supply the heat, so that heat will be divided H1 here and H2 here. So that means, shall I say that two given conductors, they are in parallel combination. So the first thing you have to understand whether they are series combination or parallel combination. So they are in parallel combination. So that's fine, right? And then, so the total H is equals to, I can write H1 plus H2. Done. Chalo. So now, what is H1 plus H2 here? So how do you write the formula in the case of parallel combination? So this is the total heat, but they are asking K equivalent, right? So directly go for the K equivalent formula. So the K equivalent is equals to K1 A1 plus K2 A2 by A1 plus A2, right? So what is K1? So let it be the inner one, the conductor 1, so the outer one, conductor 2. So the first thing is, so see here their areas are so cylindrical of radius r and areas we have to find, they did not mention. So what about their thermal conductivities? So one is K1, the inner one, the outer one is K2. So let's say the inner one area, it has the radius, how much, what's the radius of the inner one? So I can write pi r square. Inner one has radius pi r square, right? So but find the area of the second one. So this is important. Find the area of the second one. So it's a total radius minus the inner one radius, pi 2r whole square minus pi r square. Understood this part? From the whole thing, like it's just like the, so say this is a whole conductor. Just imagine. So just have a look at this one. So this is a whole conductor. So in this another, this is whole shell, another, and this is the conductor which is placed in this. So that means if you have to find the area of this shell, what we do? So the total area minus, so the inner conductor area, so that you will get the area of the remaining part. So that's what I am doing. So the total area of the given cylinder is pi into 2r whole square minus, so the inner conductor area pi r square. So if you subtract that, we get the remaining portion of the cylindrical shell. So which we get 4r square minus pi r square, which is 3 pi r square. So that's it. So now substitute the values. K1 is K1, A1 is pi r square plus K2 is K2, A2 is 3 pi r square by, so what's the A1 plus A2, pi r square plus 3 pi r square, so which is 4 pi r square. So I can take pi r square, pi r square, pi r square common in the numerator and cancel from the denominator. So I got here K1 plus 3K2, K1 plus 3K2 by 4, K1 plus 3K2 by 4, K1 plus 3K2 by 4. Option 3 is the correct one, guys. Okay, so just one thing, you have to identify in which combinations these rods are arranged, first thing, and then what is their area. These two are the major parameters in this question. Okay, so if you can identify them, you can solve the question easily. So just the formula based. So we don't need another slide for this. So let me delete this. So let's go for the question number 2. So what's the question number 2 says? So two rods with the same dimensions have thermal conductivities in the ratio 1:2. So same dimensions. So that means they have same length and so two rods with same dimension, same length and same cross sectional area. Fine. So have thermal conductivities in the ratio 1:2. So the first one is K and the second one is 2K. So then they are arranged between heat reservoirs with the same temperature. So the T1 and T2 are here T1, T2, here same T1, same T2. Fine. So that means their end temperatures are maintained same. Better. So then, so in two different configurations. So two different configurations means you can observe that in the first configuration, let it be the first configuration where, so this is the series combination and this is the second combination, so which is the parallel combination, right? Chalo, done. So now the rates of heat flow in A and B are IA, IB. So that means HA is equals to IA, HB is equals to IB. So they are asking the ratio of IA by IB. So the simple thing, first what is the formula? The HA is equals to, which is IA. What's the formula for H? H is equals to the temperature difference by the R equivalent. Yes, chala. So H is equals to, what's the temperature difference? Here T1 let it be more, so T2 let it be less. So T1 minus T2, or you can simply put delta T, because however we need the ratio only. So by the resistance, so R equivalent. So the first configuration is a series combination. The first configuration is a series combination of conductors. So there, shall I write, so the R equivalent is equals to R1 plus R2, R1 plus R2. So here R1 plus R2, what is R1, R2? So we don't know, we have to find. So here the R equivalent is equals to, so what is our R formula? You know the R formula, right? R is equals to L by Ka. L by Ka. Yes, chal. So the total length, once they are combined, so let its length be L, let its length be L. So the total length after combination is going to be 2L by, so the K equivalent into, so the area. So what's the area? Area, whole area is A. So and then here it is L by, so we don't need this, right? So we just need, so delta H. Okay, so let's find R equivalent separately. So let's find R equivalent separately. So this is R, let's say this is also, because the dimensions are same, so I can write their lengths are same, so the same K is same, two rods, thermal conductivity is in the ratio K and 2K. Okay, fine. So the R equivalent is equals to R1 plus R2, right? So if the thermal conductivities are different, so let's do one thing. So how the resistance length is same, and area is same, length is same and area is same, but the thermal conductivity is different. So R is directly inversely proportional to the K, we can write. So what I am doing is, let's write, so the first resistance of the first one, so let's understand this part carefully. R1 is equals to, so L by Ka, the first one, and the second resistance R2 is equals to, so L by the same length, so the 2K into A, L by 2K into A, right? So let me do one thing here. So let me consider this value as some R, assume, so that this will become 2R. Just assume this is R, L by 2Ka. If it is R, so then this part will become L by Ka, which is 2R. Fine, chal. So now let me use R equivalent is equals to R1, which is 2R, R2, which is R. So this whole thing will be 3R, R1 plus R2, 3, yes. So 3R is a R equivalent in the series combination. So that this comes out to be delta T by the R equivalent is what? 3R. So let it be the equation number 1. Okay, chalo. So let's do for the parallel combination. So now in the case of parallel combination, so I can write, so the R 1 by R equivalent is equals to 1 by R1 plus 1 by R2. So first let's find the R equivalent. So the 1 by R equivalent is equals to, so or else directly you can use this formula. So R1 R2 by R1 plus R2. So only two conductors are there, right? R1 R2 by R1 plus R2. So we have one is R, the other one is a 2R. The two resistors, the two thermal conductors have the thermal resistance R and 2R. So simply here R and 2R by R plus 2R, which is 3R. So R gets cancelled. So this comes out to be 2R by 3. Yes. So here we got 2R by 3 and here it is 3R. So let it be the, here the delta H will be equals to the same temperature difference by the R equivalent. So that delta T by what is the R equivalent in the parallel combination? So 2R by, so 3. So let it be the equation number 2. So this is actually the IB we got, and this one is the IA according to the given question. So now I need IA by IB ratio. So I need IA by IB ratio. So what is IA? So which is delta T by the R equivalent that we got. So 3R S by here. So the delta T by 2R by 3. Alright. So delta T gets cancelled. So I can write this one. So 1 by 3R into this will go up. Yes or no? So this part. So this is 2R by 3. Yes. So from here R gets cancelled. So 2 by 9, which is nothing but 2:9. So the correct option is 2:9. Option 4 is the correct one. So first understand the procedure. So this makes your calculations easier actually. Otherwise you have to substitute everything. So if you can assume one is R, so the other one will become 2R. So finding the equivalent resistance in the series and parallel combination will become easier. Done. If you practice more questions, you'll understand. So you'll get to know. So you have to take like this. Okay, clear guys? Understood this part? Chala, so good. So we got one more question. So let's try this question on your own. So try this question. So what's the question says here? Two identical square rods of metal are welded end to end as shown. End to end as shown. So then in the figure 1. So 20 calories of heat flows through it in 4 minutes. How much heat? 20 calories in 4 minutes. Fine. So then if the rods are welded as shown in the figure 2, so parallel combination. So this is the first one is the series combination and here it is the parallel combination. right? Chal. So then the same amount of heat flows through the rods in how much time? So here the same amount of heat, whatever the heat current that flows here, so the same amount of heat current flows through the second one. So in how much time it takes in the second case? So simple question, hope you guys can try it. So just try it on your own. Try it on your own. I'll just have some water. Done. See, in the first series combination, so let's say there are two identical rods. So if it has thermal resistance R, this also will have thermal resistance R. So because they are of the same metal, K is same, L is same, and area is same, right? So in the first case, in the series combination, so I can write, so the R equivalent is equals to R plus R, so which is 2R is a R equivalent. So then I can write, so the delta H by T is equals to Ka, or simply go for this. So what's the temperature difference? Delta T. So Q by T, H is equals to delta T by R, right? So delta T by what is R? R equivalent. Let's write this one. So what is Q? So in the first one, so the 20 calories of heat by 4 is equals to, so delta T, what's the temperature difference? So there 100, here it is 0, 100 by 0, 100 minus 0 by R equivalent is 2R, right? So this is 5 times, and then this comes out to be, let's say 5 times 50, and R remains constant, right? So 5 ones are 5 tens are. So from here, so we get R is equals to 10, right? So then, so go for the second case. So in the parallel combination, so the second one, in the case of parallel combination, so what is the R equivalent here? So the R equivalent is equals to R1 into R2 by R1 plus R2. So R plus R, right? So then, so it's 2R, sorry, R square by 2R. So which is nothing but R gets cancelled. So this becomes R by 2. So now we have to find the time taken in the second case. So we have to find the time taken in the second case. So the same amount of heat flows. So the Q by T 2, let's say the time, is equals to, so the temperature difference is same, 100 minus 0 by, so the equivalent resistance. So the R equivalent in the parallel combination. So the same amount of heat flows. So that is 20 by T2. So we have to find the time, and 100 by, so the R equivalent, which is R by 2. So right, chalo. So we can write T2 is equals to, this is 2 into 100 by, what is R value that we got? So the R value is 10, right? So then, so 10 times, so 10 into 2, 20. So 20 by T2, 20 by T2 is equals to, so this is 20, that's it. So here 20 cancel. So the T2 is equals to 1 minute. So that's what we got. So the T2 is equals to 1 minute. So because in the question they said the same amount of heat flows here. Where is that? The same amount of heat will flow through the rods in how much time? Clear guys? Understood? Clear this concept? Chalo. So let's move further. So we got one more question. So this question also I gave it as a homework in the last session. So try this now. 3 rods made of the same material. So same material in the sense K is same and having the same cross section area. So A is same and then have joined as shown in the figure. So their K is same and cross sectional area is also same. So fine. So each rod of the same length. So L, K, A. So they all are same. So if they all are same, I can say that R will be same. The thermal resistance of each conductor will be same, because R is equals to L by Ka, right? Formula. Chalo. So now the left and right ends are kept at 0 degrees and 90 degrees respectively. So the temperature of the junction. So here we have to find this junction temperature. So the simple concept. So it is at 90 degrees centigrade. This is at 90 degrees centigrade. So this is 0. So that means the heat current H1 comes from here, let's suppose, and the heat current H2 comes from this side, higher temperature to lower temperature. So let it be the temperature theta. So then these two combines and will be equals to H. So I can directly see that this is a parallel combination. So these two heat currents are coming and combining. So the H is equals to, I can write H1 plus H2. So let's write the equation for the H is equals to H1 plus H2. So what is H by, H is nothing but, so we have to find what actually the junction temperature. Okay, so we know that H is equals to delta T by R equivalent, delta T by R equivalent. So here H is, so what is delta T? Here delta T, understand the K here, H is flowing in this, right? So what is the delta T? So theta minus, this is 0 degrees, theta minus 0 by, so whole the R equivalent. So they both are in parallel combination. All the rods have same R. So right, and then they all have the R same. You need not to find R equivalent here. So H1, what is that? 90 minus theta by R. So here H2 again 90 minus theta by R. This has thermal resistance R, this has thermal resistance R, and this also has the thermal resistance R. That's it. So R gets cancelled. So the theta is equals to, so 90 plus 90, 180 minus 2 theta. So 2 theta if you bring it to this side, so the 3 theta is equals to 180. So from there the theta is equals to 180 by 3. So the 60 degrees is a junction temperature. Yes. So option 2 is the correct one, guys. Understood? A basic information, that's it. You just, I have to identify that. So the heat current from here, the heat current from here will combine and flows in the third rod. That's it. Done. Chalo. So we don't need another slide for this. So let's go for the next concept. So let's take, so the growth of ice on the lake. So see, whenever you observe the water in cold countries, especially the lake water in the cold countries, so we can see that the top layer of the water becomes ice, right? So then layer by layer, so the water converts to ice, right? So in this process, so some heat will be released when water converts to ice. So some heat will be released. So that heat will be conducted through the layers of the ice, right? So first let's say this is a lake. So this is the surface of the lake. Already some part of the water has become ice. So let's say some width y has become ice. So then, so in the very small time t, in small time dt, so let's say the dy of water has become ice. So the dy width of water has become ice. Okay. So then in this process what happens? So the latent heat of fusion, when water becomes ice, so the latent heat of fusion, so the heat will be released, right? So that heat will be conducted to the surface of water through the layers of ice. That's a process, right? So that's what I am writing here. So the Q of the latent heat, which is equals to, so the Q that is conducted. Done. So let the width of the ice that is formed is dy. So in the small time dt. Okay, chalo. So let its surface area be A. Okay, chalo. So now you know the formula here, m into L. So let's say the small mass dm of the small layer dy, so the mass is dm. Chalo. So dm into, so the latent heat of fusion is equals to, so the thermal conductivity, let it be K, so the area A, and so what's the temperature difference here? 0 degrees, here minus theta, 0 minus of minus theta plus theta. So by, so Ka theta by, so what's the length? So the already y part has become ice into, so in the small time dt. So that's it. So now what I am doing is, so let's write this mass in terms of density. You know that density is equals to mass upon volume. So from here, so the mass, small mass dm is equals to rho into v. Chalo. So the dm is equals to, so rho into, in place of volume I am writing area into, so the width, so dy. So let's substitute that one here. So I am writing here, so rho a dy into, so the length L is equals to Ka theta by y into dt into dt. So then let's write, so the rho a L into dy is equals to Ka theta by y into dt. Chalo. So let's do one thing, cancel a and a on either side, then I can write, so y dy is equals to, so k theta by rho al, I am bringing this y to this side and rho l to this side, rho l into dt, right? Chalo. So here let's integrate on either side. So let's say from y1 to y2, so y dy is equals to k theta by, so rho l into dt, so the integration of it. So from where to where? So in the time 0 to, let's say some time t, right? So chalo, it becomes, so y square by 2 into, so y1 from y1 to y2, so which is equals to k theta rho l are constants into, so the integration of dt. So the integration of dt I can write t from where to where? 0 to t. Chalo. So let's move further. So then I got, so y2 square, substitute the upper limit and lower limit. So y2 square minus y1 square by 2 is equals to k theta by rho l into the time t, upper limit minus lower limit, t minus 0 is t. So from here, so the y2 square minus, so y1 square is equals to 2 k theta by rho l into t. That's it. So this is a formula. Okay. So understand the concept so that you can solve the questions easily, guys. Understand the concept. That's it. Done. Chalo. So let's move further. So let's try to solve this question on your own, everyone. Solve this question. So what's the question says? So a deep rectangular pond of surface area A containing water, so density rho, specific heat capacity S, is located in a region where outside A temperature is at a steady value of minus 26 degrees centigrade. So the thickness of the frozen ice layer in this pond at a certain time, at a certain instant is X. So taking the thermal conductivity of ice as K, so and its specific heat, latent heat of fusion L, so the rate of increase of the thickness of the layer at this instant would be given by what they are asking. So the rate of increase of the thickness. So the rate of increase of the thickness. So that is dy by dt they are asking. Yes or no? So the same formula you can write. So the Q of the fusion of ice, which will be equals to Q conduction. So simply substitute the values now. Substitute the values. So this is the small mass, let's say dm into, so the L, right? Here K A. So the temperature, so 0 minus of minus 26, it is 26 degrees centigrade, right? So by, so dm into L is equals to Ka theta by, so what's already at this instant, so the length is x into the time dt, right? So the rate of increase in thickness, so what's the rate of increase in thickness, that's what we required. So hope you guys can solve it easily now. So I can see there are options, you can solve it easily. Chalo. So get the answer guys, final answer. Already done, it's done, it's done. Convert it to density and area. Let's say its area be A. You know this, right? Just now we did the procedure. So rho into A into, so the small width, let it be dx into L is equals to Ka into 26 by x, so which is dt. So they are asking what is dx by dt, that's it. So then what else we can cancel? Ka cancel, so the dx by dt, bring it to this side. So in the numerator here we have got 26k by, so let's write, so this becomes rho lx, rho lx. So this is what they are asking. So check for the option. So 26k by rho x, L plus 4s, no. So 26k by rho x into L minus 4s, no. So 26k by rho x square, so rho lx, option 4 is the correct one guys. Done? Clear? Chal. So then the next concept, that is the radiation. See, so the for the radiation there is no medium required. Okay, so here we are talking about the heat radiation. In this chapter we are going to discuss the heat radiation part. Okay, so here it requires no medium, it requires no medium, right? And then it is a electromagnetic wave. So as it is electromagnetic wave, it do not require any medium, right? Chalo, so let's go for the radiation concept. It's a process of the heat transfer from one place to other without heating the medium. So without heating the medium, so the heat will be transferred from one place to another place. So no medium is required for the radiation as it is a electromagnetic wave. So what is electromagnetic wave, what is their range? So all these details you'll study it in the class 12th as a separate chapter. Electromagnetic waves we have as a separate chapter. Okay, so radiation is a mixture of electromagnetic wave, so ranging from infrared to ultraviolet. So infrared, visible, and then UV. So the heat radiation we are talking about, so which is infrared, visible and UV. Okay, chalo. So from sun to earth, so whatever the heat that transfers, so the transfers through the radiation process, right? You can observe it in this diagram. Okay, na? So basic theory and theoretical information. Chalo. So this part is important, just try to understand this clearly. So Provost theory of heat exchange. So here what it says, all body emits radiation at all the temperature. So let's say if you consider a body, okay, so all bodies they emit radiation at all temperatures. So they emit radiation at all the temperatures like this. And all body absorbs heat radiations falling on it at all the temperature. Just imagine, every body in the universe emits radiation and every body in the universe absorbs radiation. Okay, but so which is a good absorber or which is a good emitter? It depends on the temperature. It depends on the heat. Let's say, so if I say if the temperature of the surroundings is greater than the temperature of the body, remember, so if I place a cold body in this room, so then what happens? It absorbs more heat because the outside temperature is more, the body's temperature is less. So as a result, it absorbs more heat. So that's why its absorptive power, the absorption is greater than the emission. Everybody absorbs and everybody emits. But so which is more or which is less, it depends on what kind of circumstance, in what kind of circumstances the body is. If you place a hard body in room temperature, what happens? It releases heat. So that means it emits. Emission will be more than the absorption, right? So that's what I wrote. If the surroundings temperature is less than the temperature of the body, this means this is a hard body. So hard body emits radiation, right? And if you place a cold body in a room temperature, so then what happens? It absorbs. Absorption is more than the emission. As a result, body temperature, what happens? So the body's temperature increases. So the body's temperature increases. So if the hot body is placed inside a room, so then absorption will be less than the emission. So the body temperature decreases. Done. And if they both are same at the same temperature, so temperature of the surrounding is equals to temperature of the body. So then absorption will be equals to emission. So the body's temperature will not change. Understood? Every body in the universe, it can absorb and it can emit. But depending on the temperature with respect to the surroundings, so the body may absorb or may emit, or sometimes its temperature might be constant with the surroundings. Equilibrium condition also might arrive. Understood this part? So the amount of emission or absorption depends on the temperature and material of the body. Important. So it depends on the temperature and material of the body also. So all the bodies do not absorb the same. Let's suppose I have some absorptive power. So this marker has some other absorptive power. Whatever the radiation I absorb, so this marker may not be able to absorb. Okay. So, but it also absorbs, but not same as of me. So every body has its unique absorptive power and its unique emissive power. Clear? Hope these statements are clear. Chalo. So then what is emissive power? So how much the body is emitting? How much the body is emitting? So that's a emissive power. So which is equals to E. So the heat energy, the heat emitted per unit area per unit time. The heat emitted per unit area per unit time is called the emissive power. The heat emitted per unit area per unit time is called the emissive power. Done, guys? Clear this part? Chal. So let's say if I take a body, so this body is emitting some radiations. So this body is emitting some radiations like this. So how much heat it is emitted per unit area per unit time? So in unit area, unit time, how much heat it is emitted, that's called the emissive power. Okay? Chal. So what are the units? What are the units of this emissive power? Emissive power E is equals to, so Q joules by area meter square time seconds R. So we can also write this as, so joule per second is nothing but watt. So watt per meter square. So this is also fine. Done, guys. So now the body emits radiation of some particular wavelength. So it might emit, so the different wavelengths. So the emissive power of particular wavelength is equals to, so the Q of that lambda by area into T. So understand. So the body might emit different wavelengths, radiations of different wavelengths. So if you want to find, so the emission power of some particular wavelength, so the heat radiated by that wavelength by per unit area per unit time. So confused? So just let me explain. Let's suppose this body is emitting, so n number of radiations. In that, let's say some green are there, some blue are there, some yellow are there. Let's say. Okay. So if you want find, so the emission power of yellow, so then the heat radiated of yellow by, so per unit area per unit time. That's it. So if you want for the green, So the emissive power of green, so which is equals to, so the heat radiated of green by per unit area per unit time. That's it. So that's what you have to understand. Even the intensity is also same. Intensity is nothing but, so the energy emitted per unit area per unit time. So that's also same, right? So the intensity or the emissive power, we can say, right? Chala. So note that point clear, everyone. So note this. Done. Chalo. So this emissive power, the emissive power depends on what? So the temperature and the wavelength. If the temperature is more, so the emissive power will be more, and so the different wavelengths emit so differently. Okay na? So this is the emissive power for a given wavelength. Emissive power for a given wavelength. Done, everyone? Clear? Chalo. So done. So E is equals to Q by T, joule per meter square second. Next. Hope this point is clear, everyone. So the emissive power formula, units, and the emissive power is different for, so the different radiations. So the emissive power for a particular wavelength, so it will be given this. So actually the temperature relation, so you can also study it from the Stephen's law. So next class we are going to discuss the Stephen's law, so where the emissive power is directly proportional to T to the power 4. So this is what the Stephen's law, like how the emissive power depends on the temperature. Done. Shall. Next. So next we have, so the absorptive power. So the percentage of heat absorbed out of total heat incident. So it's a unitless quantity, it's a dimensionless quantity. So the absorptive power is nothing but how much radiation is incidenting on the body and how much it absorbed. Let's say, simple example. So consider this is a body. So on this, so some 10 radiations are falling. Some 10 radiations, let's say. So these are the 10. So now in that, so the body is taking or absorbing only 5. Okay. So the 5 upon 10 will be the absorptive power. How many are falling on the body? Out of which, so the body is absorbing how many? So that's what the absorptive power, heat absorbed by body by heat incident on the total heat incident on the body. Let's write total heat incident on the body. Clear? So the definition is clear, everyone. Done. Shall. So it's a unitless quantity, guys. Note it down. Done. Shall. So you can do it for the particular wavelength also. The Q absorbed for that particular wavelength by, so the Q incident, the total heat incident of that particular wavelength. Let's say if you want to find, so the absorptive power for green on this body. So let's say some 10 radiations of green are falling, or else out of 10, let's say some 6 are the green in it. So in that 6, so it absorbed only 2 of the green. So that means 2 by 6 will be the absorptive power for given wavelength. So this is a absorptive power for given wavelength. For given wavelength. Done. Clear? Chalo. So then, so what is a black body? A black body is a object, so which absorbs all radiations falling on it completely at any temperature and at any instant angle. So just the theory part, so understand carefully. So the absorptive power, so is equals to 1 for the given black body. So that means it absorbs all the radiations falling on it. So 0 transmit and 0 reflection. So it absorbs all the radiations which are falling on it. So that is called a black body. Simple definition. So A for any lambda, any wavelength is going to be 1. So the zero reflection, zero transmittance. So it can absorb all the radiations falling on it at any angle, at any temperature. Okay, clear? So that's a black body. And when a perfectly black body is heated to suitable high temperature, it emits all type of radiations of possible wavelengths. So ulta definition. So the second definition, you can say it absorbs all the radiations, and at the same time, if you heat the black body so to a suitable high temperature, it emits all the type of radiations of all possible wavelengths. Done. So the example are sun and the stars. Clear, guys? So the potential black bodies, so which can be considered as the black bodies. So the lamp black, so 1% reflection, so which can be neglected, so you can consider it as a black body. So graphite, so 3% reflection, so you can consider it as a black body. And platinum or gold block is a black body. And an isothermal enclosure, so this is the most appropriate. If they gave 4 options, these are the 4 options. Let's say which of the following is the potential black body. So among them you can choose an isothermal enclosure. In different reference books also you study the same. So let's take the isothermal, where the temperature is constant, right? So then if you make a small hole, very small hole, so once you enter the light, radiations are entered into it, so then they are made to reflect inside it. So they are made to reflect inside it. Done. So if they are made to reflect inside it, so there will be no heat that goes out. Done. So this is called the potential black body. So for a perfectly black body, so its absorptive power is, what is its absorptive power? 1. Done. Chalo. So which of the following is the example of ideal black body? So you can consider blackboard, kajal, a pinhole box, none of these. So as I said earlier, so the isothermal enclosure, so a pinhole box, so a box in which so a pinhole is made. So once the light enters into it, so it will make the reflections inside it. So it absorbs completely, zero reflection, zero transmittance. Done. Chalo. So which of the following is best close to an ideal black body? Black lamp, so cavity maintained at constant temperature. So platinum black, a lump of charcoal heated to high temperature. So a cavity maintained at constant temperature. Yes, simple theory questions. So an ideal black body at room temperature is thrown into a furnace. So it is observed that, okay, so an ideal black body, it is thrown into furnace. So then what happens? It absorbs all the heat first. It absorbs all the heat. So then furnace temperature and black body's temperature becomes constant. So equilibrium. So then it emits. So at that first it becomes so dark, the completely dark. So then equilibrium condition, it appears to be bright. So first it becomes dark. So initially it is at the darkest body, and at later times brightest. So it is the darkest body at all times. It can be distinguished at all times. It is initially dark, and later at times it cannot be distinguished. No, it can be distinguished later. So it becomes bright after the temperatures has become equal or equilibrium condition. Done. Sure. So then the Kirchhoff's laws. So it's not the KCL and KVL part. So it's a Kirchhoff's law of heat. Okay. So it states the ratio of emissive power to the absorptive power for a given body, for a given wavelength at a given temperature is going to be constant and is equals to emissive power of a perfectly black body at the same temperature. So what does that mean? Let's say, so I am taking, so there is X body and so there is Y body at temperature T, and there is a black body. Okay. So now, so the Kirchhoff's law says that, so it states that the ratio of emissive power to the absorptive power of any body for a given wavelength. So the emissive power of this particular body to absorptive power of this given body, E by A of x for a given wavelength and for a given wavelength, is equals to, so at a given temperature T, so is equals to emissive power of Y body by absorptive power of Y body at a given temperature. So temperature I wrote, right? Yeah. So lambda at a given wavelength. So which is constant, and it is equals to the emissive power of the black body. It is equals to the emissive power of the black body. Clear this statement, everyone? So that means, so the bodies which are good emitters, so they are also good absorbers. That's it. So the bodies which are good emitters, they are also good absorbers. Done. So simply have to remember, so this ratio is going to be constant, the emissive power to the absorptive power, so it is constant, and which is equals to the emissive power of the black body. Emissive power of black body. So this is what, so the Kirchhoff's law says. Done, guys. Chalo. So just the theory part. So the graph shown in the adjacent diagram represents a variation of temperature of two bodies x and y having same surface area. So what with time due to the emission of radiation? Find the correct relation between the emissive power and absorptive power A of the two bodies. So all good, see here final statement. So the good absorbers are good emitters, you can write. So for whichever the one emissive power is more, for that body the absorptive power also will be more. Okay. So here, so two bodies are there. So which relation is correct? So I could see that, so the temperature of the X body is falling rapidly with time. The temperature of the X body is falling rapidly. So that means the emissive power of the X is greater than the emissive power of the Y. Emissive power of the X is greater than the emissive power of the Y. So then I can also say that the absorptive power of the X will be greater than the absorptive power of the Y. That's what the Kirchhoff's law of heat says, right? So Ex is greater than Ey and Ax is greater than Ay. So the option 3 is the correct one, guys. Understood? Chalo, so that's it from my end. So mostly the theory part. So in the next class we'll discuss, so the Stephen's law, Wien's displacement law, so which are very important concepts. So till then, keep studying. All the very best. Bye, guys.